In physics, we have the concept of forces. You might be very familiar with this. Essentially, you impart a force by pushing or pulling on an object, which causes it to change its velocity, or aka causes it to accelerate. Let's take this rock, for example. If I toss it up, I've imparted a force upon it, and then gravity, of course, is also imparting a force pulling it down. So forces, in concept, are very simple. But there are a lot of forces, right? We can talk about me pushing things, pulling things, magnets, electric fields, gravity. What we do is we can take all these forces and boil them down into 4 fundamental forces, potentially 3 even. These are forces or interactions of particles that cannot be broken down into more specific forms. These are the electromagnetic, the weak, both of which are sometimes called the electroweak together, the strong force, and of course the gravitational force. In this video, we're going to look at those 4 fundamental forces so that you understand what each of them is. Let's begin. Let me introduce you to the electromagnetic force. The electromagnetic force, also called EM for short, is the force that occurs between objects with electromagnetic charge. These are objects that have a charge of positive, negative, and that's about it. These are things like electrons, protons. This is what causes electric fields, magnetic fields. It is a force that you might be very used to in your day-to-day life. Static electricity, lightning, electricity in general. These are all related to the electromagnetic force. Charged particles create an electric field, which can go off to infinity but is only really strong at small distances. Despite that, the electromagnetic force is important both within our day-to-day life at our scale, but also very prevalent at the microscopic scale. However, once we get to large scales like planets, solar systems, the electromagnetic force is really not that prevalent. Interactions caused by the electromagnetic force are mediated by a particle. This particle is the photon, aka light. This is why it is a fundamental particle as well. Many of the forces that are fundamental have fundamental particles that cause the interactions to occur. We'll see that again in other ones. So now, let's move on to the next force. This is the weak force. The weak force is actually tied to the electromagnetic force, so sometimes instead of being treated as 2 separate forces, they are lumped into one called the electroweak force. However, since in schools a lot of the time they are treated as independent forces, we're going to do so here. The weak force causes particles to change what is called their flavor. Essentially, it causes them to change what sort of particle they are in some form of interaction. For example, muons can turn into electrons. Muons are like heavier electrons, they have the same charge, but through a weak interaction, it will decay into an electron. This is very particle physics-esque. What's important for people in day-to-day life that is different from particle physics is that the weak force is what causes interactions like beta decay. The weak force is mediated by 3 particles, 2 of which are almost the same thing. You have the Z boson, which has neutral electric charge, but you also have the charged weak particles, which are the W plus and the W minus, which are essentially the same but just with inverse charges from each other. These are the particles that interact when the weak force is occurring. So for example, in the case of the muon decaying into the electron, the muon will radiate out a Z boson and then decay into the electron and other appropriate particles to balance out this interaction. The weak force is the one that is sort of the least impressive of all of them. So now we're going to move on to a very important force. Welcome to the strong force, the most powerful force within such a small area. The strong force is what causes composite particles to stay together. That is stuff like protons and neutrons, particles that are made up of smaller fundamental particles. The strong force has a charge, sort of like the electromagnetic force, but instead of being charge-based, electromagnetic charge, it has its own thing called color charge. Color charge is different. It doesn't just have a positive and a negative. It has 3 kind of 6 charges that potentially exist. Essentially, with particles with color charge, they need to have a neutral charge to exist outside in the world. To have a neutral color charge, you either need to have a color and its opposite color, or you need 3 colors together to get what we call white light. That's why we call it color charge. It is sort of an analogy with the idea that white light is made up of red, green, blue. And so with color charge theory, we have red, green, blue, and then anti-red, anti-green, anti-blue. So you can have a particle that is a green, anti-green pair, or you can have a particle that is a red, green, blue pair. This property of the strong force, besides being what allows composite particles like protons and neutrons to exist, is also what causes those particles to group together. That's how we can get atoms. It's what allows the neutrons and protons to all sort of be bonded together in the nucleus of atomic structures. Like I said, the strong force is very powerful. In fact, it is the strongest force, but only within its small window. It dies off if the particles that would interact with it are further than femtometers apart, and if you get them too close, like less than a femtometer, in fact, it starts pushing those particles apart instead of drawing them together. So there is an interesting interaction between the color charged particles depending on their distance from each other. This kind of dictates both the size of particles like protons and neutrons, but also the size of atoms, because you have a bunch of smaller color charged particles that have all been grouped together into protons and neutrons, all sort of near each other, which causes them to bulge out in different forms. Again, vaguely speaking, the strong force is mediated by a particle called the gluon. You can kind of think about it like it glues these particles together. Gluons, unlike photons, which have no charge but cause the interaction for the electromagnetic force that is charge-based, have color charge, but they have 2 color charges. And this allows them to group 2 particles together that would be different color charges. So if you had a particle that is made up of a green, anti-green, the gluon between them is going to be green, anti-green in color. But if you had a red, green, blue, you could have a red and green gluon, and then a green and blue gluon, and then a blue and red gluon. And that would make up the proton, or neutron, whatever sort of baryon that is. So the gluon is very interesting. But with that out of the way, we've covered 3, or 2 if you want to, include the electroweak force, of the fundamental forces, and there's one more left. You know it, you love it. It's gravity. So last but not least, the gravitational force, the odd duck of the 4 fundamental forces. You might be very familiar with gravity. Essentially, gravity is caused by masses. Masses pull each other together, so anything that has mass imparts a gravitational force on all other objects that have mass. Now, I said gravity is the odd duck, and it's the odd duck for 2 reasons. One, it is the weakest of all the forces. It is essentially non-existent at the atomic scale. It is so weak, but due to that, it is very strong at sort of the galactic scale, or even at planetary scales. When we get to very large distances, the other 3 forces can't compete. So gravity is dominant. The second strange trait of gravity is that it does not have a mediating particle. This means, unlike the electromagnetic force, where we have a photon, or the weak force, where we have the Z or the W, or the strong force, where we have the gluon, there is no particle, to our knowledge, that causes the gravitational force to occur, or causes interactions related to the gravitational force. There are a few interpretations about what gravity might be. When it comes to general relativity, there is the concept of mass causes space-time to warp, and this warping is what causes the acceleration that we interpret as gravity. So some people interpret this as gravity not really being a force, it's just a property of mass warping space-time in and of itself. Another interpretation has come from trying to unify general relativity and quantum mechanics. Essentially, quantum mechanics and GR do not get along. We don't understand how gravity would work at the quantum mechanic scale, so there have been a few different attempts to try to unify this, and one proposed solution would be the existence of this particle called the graviton. Essentially, the graviton would act like a photon or any of the other mediating particles, and it would be what causes the gravitational force to occur. But as of right now, gravity is the strange, weird sibling of the four fundamental forces. So now you have a basic understanding of what the four fundamental forces are, what causes them, and where they come from. Thank you very much for watching this video. It has been a lot of fun to put together. If you like this video and you like science, especially the physics side of science, subscribe to the channel. I do videos talking about physics stuff, especially particle physics stuff, because that's what I know. There are interviews with scientists or people in the scientific community. We like science here on this channel. And a big thank you to everyone who's already subscribed. Last time I checked before recording this video, we're already getting really close to 200 subscribers. That's fantastic. As promised, I am working on a 100 subscriber related video that has to do with my research as a PhD student, but that will have to come in a little bit. So until next time, have a good one.